Pocket voltage detectors function by detecting electric fields, not magnetic fields. This is a crucial distinction to understand their operation. Electric fields are generated by the presence of electric charges, and a key point is that these fields exist even when there is no current flow. Consider a static charge. It produces an electric field without any movement of charge, which is current. When a pocket voltage detector is brought near a live wire, the electric field surrounding that wire interacts with the electric field within the detector itself. This interaction is the fundamental principle behind how the detector identifies the presence of voltage. The device is designed to sense this interaction. This interaction then triggers an indicator, typically causing the detector to light up, beep, or provide some other form of alert. This signals the presence of voltage to the user. It's important to note that the sensitivity of pocket voltage detectors varies. Some detectors are designed to detect relatively low voltages, potentially as low as 1 volt. Other detectors are configured to only respond to higher voltage levels, perhaps above 100 volts or more. This variation in sensitivity affects the applications for which each detector is best suited. For example, a highly sensitive detector might be useful for identifying very low voltage signals in electronic circuits, while a less sensitive detector might be more appropriate for working with household wiring. Pocket voltage detectors are essential tools for electricians, technicians, and other professionals who work with electricity. They provide a convenient and relatively safe way to determine whether a wire or circuit is energized. By using a non-contact voltage detector, one can quickly assess a situation without having to physically touch the conductor. This reduces the risk of electric shock. However, it is important to remember that these detectors are not foolproof. They should not be used as the sole means of verifying that a circuit is de-energized before working on it. Always follow safe work practices and use appropriate personal protective equipment, such as insulated gloves and eye protection. The presence of an electric field is influenced by several factors, including the voltage level, the distance from the source, and the presence of any shielding. A higher voltage will generally produce a stronger electric field, making it easier to detect. Conversely, the strength of the electric field decreases with distance, so the detector must be held relatively close to the source to obtain an accurate reading. Shielding, such as metal enclosures or grounded conductors, can also weaken or block the electric field, potentially making it more difficult for the detector to sense the voltage. One must be aware of these factors and take them into account when using a pocket voltage detector. Furthermore, it is essential to regularly test the detector to ensure that it is functioning correctly. Many detectors have a self-test feature that can be used to verify their operation. Additionally, it is advisable to periodically compare the detector's readings with those of a known voltage source to confirm its accuracy. In summary, pocket voltage detectors rely on the detection of electric fields to indicate the presence of voltage. They are valuable tools for quickly and safely assessing whether a circuit is energized, but should always be used in conjunction with safe work practices and appropriate personal protective equipment. Electric fields are a fundamental concept in electromagnetism. They are created by electric charges and exert forces on other charges. The strength of an electric field is determined by the amount of charge and the distance from the charge. Electric fields are vector quantities, meaning that they have both magnitude and direction. The direction of the electric field is defined as the direction of the force that it would exert on a positive test charge. Electric fields are responsible for many phenomena, including the attraction and repulsion of charged objects, the flow of electricity in circuits, and the propagation of electromagnetic waves. A changing electric field creates a magnetic field, and vice versa. This relationship is described by Maxwell's equations, which are the foundation of classical electromagnetism. The understanding of electric fields is crucial in many fields, including electrical engineering, physics, and chemistry. It is essential for designing and analyzing electrical circuits, understanding the behavior of charged particles, and developing new technologies. Electric fields can be visualized using field lines. These lines represent the direction and strength of the electric field at various points in space. The closer the field lines are to each other, the stronger the electric field. The field lines originate from positive charges and terminate on negative charges. The concept of electric fields is also used in various applications such as electrostatic painting, electrostatic separation, and medical imaging. Electrostatic painting uses electric fields to deposit paint particles onto a surface, resulting in a uniform and durable coating. Electrostatic separation uses electric fields to separate different materials based on their electrical properties. Medical imaging techniques, such as electrocardiography and electroencephalography, use electrodes to measure the electric fields produced by the heart and brain, respectively. These measurements can be used to diagnose various medical conditions. In addition to their practical applications, electric fields also play a fundamental role in our understanding of the universe. They are responsible for the forces that hold atoms and molecules together, and they are involved in many astrophysical phenomena such as the formation of stars and galaxies. The study of electric fields is an ongoing area of research, and new discoveries are constantly being made. These discoveries are leading to new technologies and a deeper understanding of the world around us. Focusing back on the pocket voltage detector, it is important to know its limitations. Firstly, the detector relies on a capacitive coupling between the live conductor and the detector's sensing circuitry. If there is inadequate capacitive coupling, the detector may not indicate the presence of voltage even if the conductor is energized. This can occur if the conductor is heavily shielded, buried deep within a wall, or if the detector is not held close enough to the conductor. Secondly, the detector may give false readings in the presence of strong electromagnetic interference. Electromagnetic interference can be generated by various sources such as radio transmitters, industrial equipment, and electronic devices. This interference can induce voltages in the detector sensing circuitry, causing it to indicate the presence of voltage even when there is none. Thirdly, some detectors may be more sensitive to certain frequencies of alternating current than others. This can lead to inaccurate readings when testing circuits with non-sinusoidal waveforms. For example, some detectors may be less sensitive to the harmonics present in the output of variable frequency drives. Fourthly, the detector's battery can affect its performance. If the battery is low, the detector may not be able to accurately sense the electric field. It is important to regularly check the battery and replace it as needed. Fifthly, the detector's environment can also affect its performance. Extreme temperatures, humidity, and altitude can all impact the detector's accuracy. It is important to use the detector within its specified operating range. Finally, the detector's design and construction can affect its performance. Some detectors are more robust and reliable than others. It is important to choose a detector that is appropriate for the intended application and to follow the manufacturer's instructions for use and maintenance. Therefore, while the pocket voltage detector is a useful tool, it is only one part of a comprehensive safety approach. Electricians should use a combination of methods to test circuits before commencing work. These methods should include verifying that the circuit is energized with a properly rated and functioning voltmeter and, if possible, visually inspecting the circuit to confirm that it is disconnected from its power source. Furthermore, an electrician should always assume that a circuit is energized until proven otherwise. This means wearing appropriate personal protective equipment, such as insulated gloves and eye protection, and following safe work practices. By following these precautions, electricians can minimize the risk of electric shock and ensure their safety. Voltage detectors can be used on various voltages depending on their rating. A detector that is rated to 600 volts alternating current may not properly indicate voltage above or below that range. One should always use the correct detector for the specific voltage range they are going to test. Firstly, when dealing with household wiring rated at 120 volts or 240 volts, a standard non-contact voltage tester designed for these voltage levels is suitable. Secondly, for industrial applications involving three-phase systems with voltages such as 480 volts or 600 volts, ensure that the non-contact voltage tester is rated for these higher voltages. Thirdly, in electronic circuits where you might encounter low voltage direct current or alternating current signals, use a non-contact voltage tester that is specifically designed for low voltage detection. Fourthly, high voltage power transmission lines require specialized equipment and trained personnel. Non-contact voltage detectors used in these scenarios must be rated for extremely high voltages. Fifthly, for automotive applications, a non-contact voltage tester designed for automotive electrical systems, typically 12 volts or 24 volts direct current, is appropriate.